Good day again, everyone. Welcome to yet another video from M.I.B. Math is Beautiful. And today we'll be looking at proofs by exhaustion. Now, proofs by exhaustion, EX, right? Now, proof by exhaustion, this is generally referred to as proof by cases, right? Proof by cases in that whenever you get the question, you'll have to look at all the possible cases that can be done on that question and prove those cases true, right? So this proof by exhaustion, it is really generally feasibly applicable to questions where there are a finite number of cases or a small number of cases. For questions where the possibility of cases are infinite, this is generally not a good way of proving if that question or scenario is true. Now, in looking at a particular question in proofs by exhaustion, let us take this one into consideration. Now, this says that prove that n plus 1 is greater than n for all positive integer less than 10. Now, to note, this sign stands for all. The sign is like an upside down A. It means for all. Isn't math beautiful? Right? So it says prove that n plus 1 is greater than n for all positive integer less than 10. In using proof by exhaustion, we'll have to look at all the possible cases of the integer where n is less than 10. So we'll have to look at where n is equal to 1, second case where n is 2, 3, and n is 9. Now we realize we stop at n is 9 because it states that we should look at all. We should actually prove this question true for all positive integer less than 10. It did not say less than or equal to, so we'll have to stop at 9. Now where n is equal to 1, you'll basically put 1 where n is, and that will be 1 plus 1 is greater than 1, which is the same thing as 2 is greater than 1, which is true. This one says where n is, you put 2, so it's 2 plus 1 is greater than 2, which is 3 is greater than 2, and there you go. And this one is 3 plus 1 is greater than 3, where greater than 3. So if we actually look, you realize that all the cases here are true for where n is an integer that is less than 10. Therefore, for all positive integers less than 10, the statement of n plus 1 is greater than n is indeed true. Now, isn't math beautiful, people? Math is indeed beautiful, and this was a question excellently done. Now, the key thing to note is that for all of these questions, you'll actually have to think about all the possible cases of the question and actually exhaust all of them, meaning you work all of them to prove that they are indeed true. And if they are indeed true, if everything holds true, then you finish with your conclusive statement, which could have been in a worded form as well. It doesn't have to be in mathematical notations as I have done here. We will actually look at another question before we go. Now let us look at the other question using proof by exhaustion. Now this question states that we should prove by exhaustion that if n is an integer, then 3n squared plus n plus 14 is actually even. Now looking at this question, there are actually two cases, and those two cases are where n is an element of integers, where n can be an even integer, or n can be an odd integer. Now to note that denoting positive and odd integers, the general form is where n is equals to 2k, 2k denoting an even number, or n is equals to 2k plus 1, where 2k plus 1 denotes an odd number. And this is really standard in that whatever k is just a number, an integer. So if k is 1, 2 times 1 is actually 2, which is an even number. If k is 3, 2 times 3 is 6, which is an even number. Same here. If k is 1, 2 times 1 is 2 plus 1 is 3, which is an odd number. And if k is 2, it would be 2 times 2 is 4 plus 1, which is 5, which is still an odd number. So these are general notations. Now looking at case 1, which is where n is equals to 2k, which is an even number. So we are trying to prove that 3n squared plus n plus 14 is actually even. Now let us look at this. 3n squared plus n plus 4, right? If we are to take n equals 2k and substitute in this equation, we would actually get 3 times 2k all squared plus 2k plus 14. And this boils down to basically 12k squared plus 2k plus 14. Now, if we are to factorize this equation, or rather factorize the equation with 2 being the common between all the three coefficients, then we'll actually get 2 times 6k squared plus k plus 7, right? Now, if we are to look at this, we can see that 3n squared plus n plus 14 is equals to 2 times, all brackets, 6k squared plus k plus 7, right? Now, this format here is similar to what 2k is. 2 times a number. If this is an integer, then 2 times any integer will always be even. So thus far we actually proved true that 3n squared plus n plus 14 is actually equals to 2 times an integer, which is 6k squared plus k plus 7, which is even. So let us simplify this. This can be equals to 2 times another number. We're going to call it a, where a is equals to 6k squared plus k plus 7, right? Which is an element of integers. So here we can see that since 6k squared plus k plus 7 is an integer, therefore 3n squared plus n plus 14 is actually even, because it's 2 times a number. 2 times any number will always be even. So already we prove it true. Now looking at case 2, where n is equals to 2k plus 1, right? It's simple substitute. 3n squared plus n plus 14 is equals to 3 times 2k plus 1 all squared plus 2 times plus 2k plus 1 plus 14, and this will be 3 times 4k squared plus 4k plus 1 plus 2k plus 15. So expanding this would be square root of 2 4k squared. 2 times 2 is 4k plus 1 squared plus 2k plus 15, and this will actually simplify to 12. That would be what? 12k squared plus 14k plus 18. So 3n squared plus n plus 14 is equals to 12k squared plus 14k plus 18. Again, we can factorize the right hand side with 2 being the common factor, and taking that out, we get 2 times 6k squared plus 7k plus 9. Again, 6k squared plus 7k plus 9 is indeed an integer. Therefore, since 6k squared plus 7k plus 9 is an integer, therefore 3n squared plus n plus 14 is 2 times an integer, we'll call it b this time, which is indeed even. So when you actually look at both cases, you realize that both cases proves true. So since both cases proves true, therefore for all n, which is an element of an integer, 3n squared plus n plus 14 is even. Question excellently done. Math is beautiful. Thanks again for watching. Please like, subscribe, hit the notification bell, and leave your comments as needed.